Hi, everybody. Welcome back to Chem 121. It's not often that we have to use the Wednesday day for a lecture. Oops, I almost hit the wrong button here. But sometimes I do want to use it just so that we don't fall behind. I think it's better to have an extra video up that you can watch at some point, even if you aren't here for the lecture. Which is totally okay, because this is basically an online class, right? I think that it's better to just have a video up here that you can watch at some point before the midterm, rather than just go it on your own at the end of the Chapter 5 stuff, and because that's no fun. And pushing back the exam doesn't help us, unfortunately, because we still have to get through all the content for the next exam. So sometimes I will have to throw a extra lecture in here and there, and I do appreciate if you were able to come out today that you did. I also want to go over today lab number 2. Now, lab number 2 is... Oh, I should probably capture it. Hold on. Let's do that first. Oh, but before I do say that, I do want to mention down at the bottom, quiz number 2 due tonight. Make sure you get that in by the deadline. It closes 24 hours later. Quiz number 3 is due Monday. And then when we're done with this, quiz number 4 will be due Wednesday of next week. So, yeah, lots of stuff coming up next week. Next week's going to kind of suck. I was just going to talk to Maya, and she immediately left. She's sitting here going, meow, you don't pay attention to me. Maya. No, she ran away. Okay. Okay, so I do have that captured, so I don't know what this will look like. Yeah, that's not great. Alright, so this is probably okay for now. We'll just do this. Okay, so lab number 2 is all about physical and chemical properties, and we talked a little bit about this in chapter 1, where I had you ascribe either chemical or physical to a description. So, like, grape soda is purple. Well, that's physical because looking at the grape soda does not change it. But setting gunpowder on fire would be chemical because you can't get the gunpowder back and use it again without tremendous effort. So, what we have here is a series of videos. Wow, everyone is meowing here. Oh, there's Maya. She's back. Maya. Maya, come up. Come say hi to the class. She really wants to. What lab number 2 is a series of videos that I'm going to ask you questions about. And those questions are in this worksheet here. So there's just a lot of questions. Oops, this didn't quite fit on the screen, though. So this is worksheet number 2. And it's just a lot of questions about the video that you see. And then if you go down to the analysis questions, which you can't see at the bottom, but it's just the next tab. There are a few other questions that ask you to just go over... There's only 4 of these. There's a few other questions that ask you to go over, like, conceptual stuff, like the overall purpose. Yeah, I heard that Discord is down, but at the same time, I'm still connected in 2 places, and it seems like it's working to me. Like, I didn't get a message that said that my message could not be delivered to the class when I sent the, hey, the lecture is up. And I received a message at, well, that was 11:21. Let me see here. I see some other people sent me messages at like 11:50, so I think it might be working. I don't know. Anyway, what I want you to do in this, what I'm going to do really quickly. So there is a series of videos. If you go into the modules tab, I guess I could check it this way too. And you scroll down to lab number 2. It says videos for lab number 2. So there are so many of these that I linked them in there. Oops, I got to do it this way. Yeah, I linked them in a separate playlist. So here are the 4 videos that I have specifically for this lab. So this one is the combustion of mercury thiocyanate. And you can kind of see what's going on here. It looks a lot better in the video. I'm not going to play the videos because I don't want to spoil this for you. The second one is a water electrolysis video. Water is very, very stable, but if you do specific conditions, or under specific conditions, you can split it back into hydrogen and oxygen. And one of those is electricity. And then the third one is a how it's made video about the construction of aluminum cans. And then finally, a fourth one is a home science done by, I guess her name is Primrose Kitten, which is a hell of a name, I have to say. That might be a name that would qualify for, like, I would name a daughter Primrose Kitten. Like that's just classy right there. But it involves rusting iron nails under various conditions. So what the scientist does in this video is she tries different things. So she just tries putting a nail in water, then putting a nail in water with salt, then putting a nail in just like cooking oil, and then putting a nail in water, but putting oil on top of that so that the oxygen can't get in, and seeing what the conditions actually are for rusting. And so I ask you several questions about that. If one of these videos doesn't work, let me know immediately. I did have an issue one quarter where a video that I linked got taken down and it was no longer available, and I had to make a change. That does happen. YouTube is not as permanent as I would like it to be, but it looks like everything is here, so this should be okay. And that's really all I have to say about lab number 2, is watch the videos and then answer the questions. I do give you timestamps for the videos, so you don't have to watch the entire 5-minute video, although it's how it's made. I don't know if you've ever seen how it's made. It's really freaking cool. And this one is just like aluminum cans. Like, there's a how it's made for like virtually everything that I can think of, because I used to just watch it. Like, not religiously, but if it was on TV, I'd sit down and watch it, which is very, it says a lot. I don't actually watch TV at all because I just don't have time or desire. But I would watch how it's made just because it's so cool. It's like along the lines of Mythbusters. If you like Mythbusters, I feel like how it's made would also be a very good analog to that, I guess. Less science, but more like practical and engineering and stuff like that. Okay, that's all I really have to say for lab number 2. So if you have any questions, make sure to ask me in the Discord on when it works. Can you find these videos on the module? Yeah, so... Oh, I just closed the window. Hold on. Reopen, close window. Okay, that did work. That's good. So if I do this again... Boop. Oh, I can't find it because I closed the window, so I had to open the window again. Boop, there we go. So under lab worksheet 2, these are the worksheets, and then I have this video list for lab worksheet number 2. The other thing I can mention about this is that these videos are also linked in the documentation. That's not the documentation. In here, so if you are wondering what video goes to what part, it will tell you right here. So video number 1 is part 2 is mercury thiocyanate. So that's the first video. And then questions 3 and 4 are water electrolysis, and then so on and so forth. So all the documentation tells you all that. So, but yeah, if you have any questions, let me know in the Discord again when it's working. I may have heard of periodic videos. Is that the scientist guy who looks kind of like Dr. Wily, I want to say, except he's very obviously not chaotic evil. Because that's also a very good channel. There are a lot of really good science channels on YouTube, and I've watched very little of them because I already know everything about chemistry, basically. Other than, like, cutting frontier stuff. So and I'm not saying that in jest or, like, to be, like, arrogant about it. It's that when you study something for, like, 11 or 12 years, yeah, you learn all of it. Like, I know 95% of what is taught in college about chemistry. The other 5% is, like, in labs and research and stuff, so... which is kind of the beauty of college, and that is we've taken hundreds and hundreds of years of chemistry and distilled it all down to something you can learn in like 10 weeks. All right. I don't remember if we did these examples. I want to say that we didn't yesterday. But what we're going to do for this is we're going to figure out what ions are formed using the octet rule. So, for example, calcium would form this ion, and chlorine would form this ion, and then I'd balance the charges to figure out the ionic compound. So, if you remember yesterday how we did this, so the way that we determine that this is what I need to do is that calcium has 2 valence electrons because it's in group 2. I would get rid of those to make it calcium 2 plus. Chlorine has 7 valence electrons. It needs 1 more to become Cl minus. So we've got our octets. Now I just need to have enough atoms with octets so that I can balance out the charge. Okay, so that's what I want you to do. If you've already done these, go ahead and just type your answers in the chat. I, again, don't remember doing these, but I'm going to give you like 2 or 3 minutes just as a little warm-up to do these exercises. We'll go over the answers in just a bit, and then we're going to talk about naming stuff, which is we're going to spend the first hour doing. Okay, see you in a bit. 1 or 2 more minutes, we'll go over the answers. All right, let's go over the answers here. I need to go to this screen to do this, though. That's fine. Pen, there it is. Okay, so if we look at magnesium, which has 2 valence electrons, in order to make it an ion, I would have to get rid of those to satisfy the octet rule, right? And so that would give me this as my ion for magnesium. How about oxygen? Oxygen's in this situation where it has 6 valence electrons. And in order to satisfy its octet, I'd have to give it 2 more. And now I just have to balance out the charges. Well, I have +2 and -2. Those balance out, so the compound that I should form would be magnesium oxide, MgO. All right. How about the next one? So I got sodium, which has 1 valence electron. Let's just chuck that to give it an octet. Then we got phosphorus, which has 5 valence electrons. We need to add 3 electrons in there to satisfy its octet. And then I just got to balance the charges. Well, I have +1 and -3. That's not going to balance out, so I got to do this. So now I have +3. 1, 2, 3. We'll just do this. I have -3 down there. So there we go, Na3P. Remember that what goes in your formula is how many you used. The charges will get you to that point. When you are writing the formula, the charges should never appear. So notice how these formulas that I have are neutral. So no charges in the end formula. So just be aware of that. Don't keep the charges in there because they're neutralized, right? They're all gone. I mean, they still exist, but they've been canceled out by other charges, so they don't have an influence on other things. They're tied up, in other words. I just realized that what I just wrote is going to get scrolled off the screen, so pause the video if you need that, and there it goes. All right, so beryllium here. Beryllium looks like this. Now, beryllium doesn't get an octet, but it only has 4 electrons, and getting rid of these 2 leaves it with just 2 that look like helium, and that's good enough. So remember that small atoms don't actually get to look like noble gases with 8 electrons. They have to resemble helium because that's just the closest that they can get to a noble gas. They have too few electrons. Fluorine here has 7 electrons. We're going to add in one to make it that. I have +2, but I only have a -1, so I got to add another one of these. And there you go. And then finally, for aluminum and sulfur, aluminum's got 3 valence electrons. Let's just chuck them to make aluminum 3+. That'll have an octet. And then finally, we have sulfur, which has 6 valence electrons. We're going to add 2. So there's 1 and there's 1. And now I got to balance out these charges, which is kind of cumbersome because adding one of one or the other isn't going to solve the issue. If you're ever in an issue like this and you don't know like how to make this work out, try multiplying the charges together. So what's 3 times 2? Well, it's 6. So try and get both to 6, which would be, okay, I'll do this. So that's 6. And I'll do this. That's 6. And it'll work. So if you ever have like an odd number issue where it's like, well, these don't divide evenly into each other, multiply the charges together and then try to get both sides to that number. Because you'll be able to, because that's how multiplication works. That's the power of numbers. All right. There you go. Very good. Let me know if you have any questions on how to construct ionic compounds, because now that we know how to do that, in this next section... Oh, there's the homework practice. I wish those just showed up automatically. Now that we know how to do that, you're going to have to do that on your own in order to solve naming problems that are coming up here, because you're going to get like a word, and you're going to have to turn that into a formula, and you're going to have to deconstruct the words into ions into a formula by doing what we just did. So it's more or less the same thing with an extra step. Now, in case you were curious, and I believe that I showed this picture earlier on, this is what an ionic compound looks like. It is just a repeating array of ions over and over and over and over and over. And they are not molecules. This is why we can't say molecular compound for ionic. We have to say ionic compound instead. And the difference here, in terms of ions collecting together, is that there's a ton of them that are all attracted in all directions. Whereas with molecules that you're going to see when we get to, or if you recall from the previous lecture, actually, all the molecules are independent, even though there's tons of them. There's spaces between them, and they can move past each other and go on their merry way. These are all basically stuck here. All these pieces are like little mini magnets that are all connected to each other. So the simplest repeating pattern is the formula unit. That's where the formula comes from. I am greatly oversimplifying here by just circling a sodium and a chlorine. But for our purposes, if you just imagine like the smallest piece that you can copy and paste to create the entire lattice as the formula unit, that's good enough. In reality, you have to draw like a cube that has portions of atoms that you could copy and paste over and over and over. But because spatial thinking is not something that is very easy to do without drawing a lot of complex diagrams for ionic compounds, we're just going to glaze over that. And all you need to know is that the formula unit is just whatever you can copy and paste, that's the formula of the ionic compound. All right, let's talk about naming these things, because that's the last thing that we had to do in Chapter 4. I put my stylus in the wrong spot here. Why isn't this working? Oh, because I got to click on it. There we go. I clicked on something else, I think. All right. The first thing that we're going to do is we're going to define a binary compound. A binary compound has only 2 elements present in it. In order for something to be binary, you can only have 2 elements. You can't have 1, and you can't have 3. And that makes sense because that's what the term binary means, right? In computing, binary is 0 or 1. Really, what that means is 2 different states are available. So on the screen here, you could see that these compounds both have 2 types of elements. Now, what's important to note is that they don't have 2 atoms. So NaCl is binary because it's got 2 elements, sodium and chlorine. But CO2 is also binary because it still has 2 elements, carbon and oxygen. There's just multiple oxygens. That doesn't matter. We only care about the number of elements present, not the number of atoms of any elements. Now, in order for us to be able to name a compound in this class, it has to be binary ionic. For something to be binary ionic, it has to have 2 elements, like we just said, because it's binary. But it also has to be ionic, and we're going to define ionic compounds as the following. One of the elements in the compound is a metal. The other is a nonmetal. By now, you've probably noticed that all the metals live on the left side of the periodic table, and all the nonmetals live on the right. And you've probably also noticed that all the elements on the left want to give up their electrons to achieve an octet, and all the elements on the right want to accept electrons to complete their octet. Thus, you could conclude that, metals give away their electrons, and nonmetals accept electrons. And there you go. That's how you make an ionic compound. Something gives away electrons, something accepts them. The something that gives them away is the metal, the something that accepts them is the nonmetal. So, if I give you a compound, the first thing you want to do is look at it and say, is it binary ionic? And so I would say, well, it has 2 elements, so the binary part checks out. And then one is a metal, and one is a nonmetal. And so the ionic part checks out. So the conclusion we would say is, yes. Yes, it is. All right. What I want you to do, I'll number these for you. I want you to tell me which ones are binary compounds and which ones are binary ionic. Because again, this is going to be the first question that you ask yourself whenever you do a problem on naming. Is it a binary compound or binary ionic? There is a third type that we're going to talk about at the end of this chapter, which is a sort of special case. But go ahead and categorize these. I'll give you like 1 or 2 minutes because it shouldn't take that long. And then type your answer in the chat. All right, 1 more minute. All right, so what I'm going to do is in yellow, oops, if I could, I'll just click on it. I'm going to highlight the metals in yellow. And so the 1, 1, 3, and 5 here are binary ionic. And 2 and 4 must therefore be binary. There you go. So your first step is always going to be, for any problem that asks you, hey, what's the name of this? Is it binary ionic or binary? Later on, we're going to add an extra word to this. And these are going to be your categories, because the rules for naming compounds will differ. We're going to work today on the rules for naming these guys. And then this is Chapter 5. We're going to talk all about binary molecular compounds a little bit today, and then mostly next week. Do you treat semi-metals as metals? If you mean metalloids, those tend to be non-metal. They tend to be treated like non-metals. However, it does depend. There is a property that I have not disclosed to you yet that actually dictates, like, as a numerical value, whether you call it a metal or whether you call it a non-metal in a compound. And then the difference between the two numbers actually dictates a rule. Metalloids tend to be kind of in the middle, of course, in a gray area, and it depends a lot more on what that value of that number is. So we'll get to that next week. It's called electronegativity if you are reading ahead. And we'll comment on that a little bit more in Chapter 5. For now, we'll treat them as nonmetals if they come up. All right, so what we're going to do is we're going to start giving names to stuff. You can't just pronounce the letters in sequence. So that's not a thing that you can type into Canvas, for example. So if I say, like, what's the name of NABR, and you type in NABR, it'll mark it wrong, obviously, because these things have names. So we're going to use an algorithm, and the algorithm is shown on the screen below, and it is deceptively simple. I didn't mean to make that mark there. You're going to name whatever the metal is, and you're going to name whatever the non-metal is, but stick "ide" on the end of it. So you've probably heard "ide," maybe in things like carbon dioxide, things like that. Carbon dioxide is not an ionic compound, so it would not follow this pattern, but "ide" is a very common ending for elements. And the reason for that is because elements that end in "ide" are anions. So for example, we'll show that in a second here, because we're going to go through some examples. All right. Name the metal. The metal's name is literally what's on the periodic table, with some extra information attached depending on the circumstance. Okay? Now, this is really relevant. If the metal is in group 1A, 2A, or is aluminum, you just use the metal name by itself. Depending on the textbook you are using, there are additional elements that are included in this. I only am going to require that you know that these elements, groups 1A, 2A, and aluminum, and if you're not using the A notation, these are just groups 1 and 2. Or aluminum. Aluminum, which is by itself, often column 3. We're gonna name these with just the name. And the reason for this is because the charges that they adopt follow the octet rule. Ooh, my W got away from me there. Now, because they follow the octet rule, the charge that they get is always the same. So, sodium is always Na+. It will never be anything else. Aluminum is always aluminum 3+. It will never be anything else. Barium is always barium 2+. It will never be anything else, because they follow the octet rule. Other elements, though, such as transition metals, don't follow the octet rule, which means that they can have any charge that they really want to. Some charges are more common than others, but for instance, both of these exist, iron 2 and iron 3+. In fact, iron 4+ exists too. You can't just call them all iron, though, right? Up here, it makes sense. I could just say sodium because this is the only sodium I will ever see, sodium +1. But if iron 2+ and iron 3+ and iron 4+ all exist, I have to distinguish them and give them different names. And the way that we do that is we assign a Roman numeral that represents the charge. So this would be iron 2, this one would be iron 3, and this one would be iron 4. Do we all know the Roman numerals up to 10? If not, then we got to go over here. And you know what, let's just go over them anyway, just in case. Roman numerals are only used in 3 instances on Earth. One is the Super Bowl, which is coming up, I hear. What are we on, Super Bowl, like 53? So it's probably like LIII. In fact, I should look that up, just so I don't look like I'm a total dunce. Super Bowl 2022, which is in 2 weeks. Oh, we're on 56. Okay. And of course, the characters that it says for the Super Bowl are LVI, which is 56. So that's where we use that's where we use Roman numerals. Is 1, the Super Bowl. 2, Final Fantasy games. We're up to 15 on that one. 16 is supposed to come out fairly soon. And then finally 3, naming ionic compounds. The third one is most relevant to us, but the other 2 are interesting on their own. All right, so what I'm going to do is I'm going to list, so the Arabic numbering system, which is what we use, and then the Roman numbering system, which is stupid. The Arabic numbering system is base 10, which is awesome. I ran out of space, but that's okay. Actually, I got to make sure that this doesn't scroll off. Okay. So for the Roman numbering system, 1 is the letter I, because it looks kind of like a 1, I guess. 2 is II. 3 is III. You can either use the top bars or not. I tend to do it when I'm doing this example, and then I never do it again for some reason. 4 is IV. 5 is V. 6 is VI. 7 is VII. 8 is VIII. Oops, I put too many. 9 is IX. And 10 is X. Those didn't line up very well, but I mean, you can count them in number order, so it's fine. And then again, if you want to just write them like this instead, that's totally fine. In fact, this is what they're going to show up on your computer as anyway, when you type them in. So that is perfectly acceptable. Over here. There we go. All right. So what that requires you to do is you're going to have to figure out what the charge on your metal is and then assign it the correct Roman numeral. Now, the convention for typing is very important. The first thing that you're going to notice, I'm going to hit clear here. And I'm going to write 2 things on here that you must be aware of, or else Canvas will mark everything wrong. Element names are not capitalized. I sort of ran out of space there at the end. Let me erase that and we'll write it again because I want to make sure that you don't make this mistake. Never capitalize the name of an element. Elements are not proper nouns. If you capitalize the name of your element, for example, if you typed in iron with a capital I or platinum with a capital P, you will get marked wrong, and I won't be able to give you your credit back because element names are not capitalized. This is the most pedantic thing I do in this class, other than sig figs, is don't capitalize element names. If you do, it's wrong. When you are writing the name of the metal, don't put any spaces. So don't put a space between platinum and the parenthesis, nor should you put any spaces inside the parentheses. Type it all as one word. So if I wrote iron space 2 parentheses II parenthesis, Canvas would mark it wrong because it is not expecting a space. Because there are no spaces. It treated it all as one word. Okay, this is the convention that is used for naming metals. Be very careful about it because everybody screws this up once or twice. Especially when you're writing it down, you'll just be like, oh, okay, it doesn't look like a space, but if it looks kind of like a space, I have to mark it wrong. And Canvas will know because you'll actually hit that giant long key in the middle of your keyboard when you do that. So be careful. The tendency to want to put spaces in here is real, as is the tendency to want to capitalize. Don't capitalize. You'll notice that on some of my slides here, I'm just going to skip ahead, that it looks like, oh, he capitalized the first thing. This is because it's the beginning of a sentence, and it is not intended to be capitalized, okay? So you do follow proper grammatical rules if you start a sentence, but if you are just entering a name in a blank, don't capitalize it. So I'm going to write that. Only capitalized because it's the beginning of a sentence. So don't actually capitalize anything. The thing that you do capitalize is your Roman numerals. Your Roman numerals should be capitalized because that's how we represent the Roman numerals. We use uppercase letters. All right, that's metals. Probably didn't think that was going to be that complex, but here we are. Non-metals, a little bit easier. What you're going to do is you're going to take your name of your element that is a non-metal, and you're going to tear the end off and put "ide." And you've probably heard most of these. In your textbook, they are on table 4.2. And what I'm going to do instead of assuming that you have your textbook is I'm going to just go back over here to this screen, and I'm going to just write them all out for you. So let me clear all this off the screen. And let me get a periodic table so I know which ones I should name. So I'm going to start in the top right, and I'm going to work my way to the left. So we've got fluoride, got chloride, got bromide, iodide, and then going, so this is group 17. And then in group 16, we've got oxide, sulfide, and selenide. I mean, telluride exists, but we're probably never going to see it. And then in group 15, we've got nitride. Oops. Phosphide. And then arsenide, same thing, probably not going to come up. I'll write it down just in case. And that's really it. So carbide does exist, but it doesn't follow these rules. Carbide's actually a polyatomic ion. So those are the ide elements that you're probably going to see for this class. And there's only like 10 of them. Now, the "ide" represents that these are ions, specifically anions. So you can see here that chlorine without a charge ends it with its normal ending. But chlorine with a charge ends in "ide." And the ions that these form, actually, I shouldn't write this as brackets. The ions that are formed always follow the octet rule. So no numbers are needed. You do not need any Roman numerals for the nonmetals because they all follow the octet rule. So you just write whatever element it is with "ide" on the end for its name. And then in your mind, you should go, okay, it's however many electrons are needed to make the octet, and then that's its charge in minus. So chlorine needs one additional electron to become chloride with an octet. All right. That's the naming convention. So now our job is to put all this information together. So let's do this. So I'm going to just clear this off the screen. So what would I call this? I mean, even though I've already got the answer that is shown up here, what you would do to name this substance is you would say, okay, what is this? Is it a metal or non-metal? Well, it's a metal. And is it in group 1, 2, or is it aluminum? K is, and according to the periodic table, its name is potassium. So I would write that down. And this is bromine. We would add "ide" to it. Brome, "ide," and there's your name. All right. What would I call this? I'm going to give you like 20 seconds to think about it. Type your answer in the chat if you'd like, and then we'll go over it. All right, let's look at the answer here. If I could find the stylus, there it is. So this element is in column 1, group 1. So it would be sodium. No numbers are needed. O is oxygen, but I'm going to chop off the end and type in "ide," oxide. Now, importantly, there are no numbers in the formula that get put in the formula, or in the name, I'm sorry. So this 2 here, you just ignore it. And the reason for that is the rules that we posted, these rules right here, say nothing about numbers of elements. So it doesn't say if you have 2, put something in the name. It doesn't say if you have 7, put something in the name. You're literally just naming the metal and naming the non-metal. Okay, so be careful about that, because later on in Chapter 5, the number is going to matter for binary covalent compounds, or binary molecular, I mean. But here it does not. We are totally just going to ignore the number of atoms with regards to the name. All right. Let's suppose that you had a formula that was consisting of these ions, CO2 plus and Cl minus. What would the formula be, and what would its name be? So type both into the chat, and I'll give you a minute to do that. All right, let's go over the answer here. So if I was to write down the name of this ion, it would be cobalt 2, not capitalized, and no spaces. And then this is chloride. So there's its name, cobalt 2 chloride. Now I have to write the formula for it, where I would just write out the ions here. And we would do the same thing that we did before. Does the charge balance out? Now I need an extra minus here, right? So I can get 2 plus and 2 minus. And so this would be the formula. Be really careful. This O right here does need to be lowercase. If it's capitalized, then you'll have a carbon-oxygen-chlorine sort of thing. Which does exist, actually. Capital C, capital O, Cl2 is a compound. So just be mindful of that. But yeah, this is cobalt 2 chloride. All right, I just looked at the clock and I went over the time for the break. So what we're going to do is I'm going to put this on the screen here. We're going to take a 10-minute break because we are due for that. Let me get the timer on the screen. And when we come back in 10 minutes, we will continue naming stuff and we'll finish off the chapter. Oops, I got to click this away before I can do that. And let me go find us a good song. If I turn on the audio, that would probably help. Alright, we're back. I'll just wind this down here. Hope everybody had a good break. Top up your water, pet the cat, you know, that sort of thing. Alright, so I'm going to give you another example here. This one uses Mn2+ and O2-. It's really hard for me not to just say the ions. I almost did. So I want you to do the same thing. I want you to tell me the formula that you would construct out of this, and also its name. And this is actually an important exercise, because you're going to have to do both of these things for all of these problems. Generally speaking, I'm going to either give you the formula or the name, and this step that's on the screen here is the intermediary sort of step. So knowing what the ions are is crucial. So go ahead and tell me, what's the name and what's the formula? Alright, let's go over the answer here. So the formula should be pretty straightforward, because there's +2 and -2. So you just write MnO, PQRSTUV WXYZ. No, I'm just kidding. Just MnO is fine. And then we just got to name what these are. So this is manganese 2. And this is oxide. Now be careful, again, don't put spaces in there, and also don't capitalize, because Canvas will mark them wrong, and I'll have to shrug, which is real unfortunate, because it's a really innocent mistake to make. I know everybody wants to type and capitalize stuff, but don't resist the urge to do it, because it will get marked wrong. All right. Now, for some compounds, which are going to be the ones that we use on page 2, you're going to have to figure out pieces of them. So we'll start on page 1 here. I'm going to number these. And what I want you to do is turn the top list of formulas into names. So you need to give me the name of each of those. And for the bottom list, I want you to give me the formula. Okay? Now, the steps to doing this, you're always going to have to go through the ions. So for number 1, for example, I would split this into the ions that it is formed from, and then I would name them. So this is lithium, and then the O is oxide. So there's the first one for you. Start by breaking them into ions. That's always a good first step. How do you know what ions they should break into? Well, you know how the octet rule works. So you know how many electrons they should start with and how many they should end with to get to their octet. On the next page, we're going to run into a different issue with transition metals, though, and we'll talk about that. Like, what do you do when you can't use the octet on some things? I'm going to give you 5 minutes to do this. We'll go over the answers when that time has elapsed. So see you in a bit. I don't want to give people too little time here, so go ahead and type out any answers that you have, and then we'll go over the answers like about 2 minutes or so. All right. Let's go over the answers here on this screen. Oops. I need the top ones. There we go. All right, we probably don't need this anymore, so I'll just clear it. All right, so I'm going to split all these into their ions. At this point, we should know more or less where the ions come from. Again, the octet rule. But if you're confused, let me know, and I can go over the example there. So this is beryllium chloride. I lost the D there because I guess I got to reboot Photoshop or something. Probably Chrome eating up all my RAM. So there's my aluminum and my oxygen ions there. Something I do want to note, I'm going to write this in blue here. If you are British or Canadian, your spelling of aluminum has this blue I in it. Aluminium. I believe that the video for how it's made will actually pronounce it aluminium, because I got the clip from, I want to say, the UK. I may be wrong on that. If you use either of those spellings in Canvas, it'll accept both, because I've programmed it to accept both the American spelling, which is aluminum, and the British spelling, aluminium. Because a lot of people don't notice that on the periodic table I hand out, because the one I use in class is British. For some reason, I didn't know this when I printed it. I made 100 of them, and I laminated them. And it says aluminium on it. So just FYI, in case you were curious and had questions about that. I also accept the alternate spelling for sulfur, which is this, as opposed to this. Either of those is fine. That's not what I wanted to do. I wanted to do that. Boop. There we go. All right, next one. Potassium iodide here. So K plus, I minus. Potassium iodide. There you go. All right, and then for 5 through 8 here. So let's write the name out. Strontium bromide. Strontium is this. And then bromide is that. And now I just got to balance out the charges. I got 2 positives, 1 negative, so I need another negative. And there you go. We got rubidium nitride. Oops. There we go. So here's rubidium nitride. And then I need to balance out the charges. Well, I have 3 negatives, so I need 3 positives to counteract it. So I got to go like this. And we'll put it all together. RB3. N. We got sodium. Oops, hold on. Sodium. I'm writing out the names, not the formulas. Sulfide. So sodium is this. Sulfide is that. I need another sodium to counteract the charges, so I've got 2 positives and 2 negatives. Na2S. And then finally, magnesium iodide. Magnesium is 2 plus. Iodide is minus. Need another of those. And there you go. All right. Looks like most people got all of this right. Very good. Excellent. All right. Let's do the next set here. So we'll go to the next page here. So in some cases, you have to solve for what the charge is. So for instance, if I gave you, instead of these formulas, let's suppose that I gave you or instead of the ions, let's suppose I gave you this. And I said, what would you call this? Well, I know there's a cobalt in there, but I don't know what charge it is, because it could be variable, right? But I do also know that I have 3 bromides, and bromide is always -1. Because of the octet rule, yeah? Okay, so what goes in the blank to counterbalance all the charges? And the conclusion that you should draw is that this is 3 plus. And so this must be cobalt 3. I don't know why it does that. Cobalt 3 bromide. So if you see a formula, you may have to go back and figure out what the charges are by doing a little bit of logic. And you will always be able to solve for the positive charge because the negative charges are always going to follow the octet rule. So using your nonmetals, you can figure out what the total minus charge is, and from there deduce the positive charge. Now for these examples, I have given you the ions. So what I want you to do is take those ions and put them into formulas. You don't have to do the first one because I just did it. We'll number these again. And I'll give you 5 more minutes to try them. Okay? Again, be careful of spelling. Make sure that you don't add extra capital letters or spaces. We'll go over the answer in about 5 minutes, so see you then. All right, 1 or 2 more minutes. Go ahead and type anything you got in the chat so I know where you're at. All right, let's go over the answers here. Boop. We'll just put those 2 up here for now. Erase everything. And then home. No, page up. No. None of that did anything that I wanted. Okay. All right, so we got Ti4+ and O2-. And I need another O2- to balance out the charges here. And then I need to name it. So this is titanium. Oh, frickin'. There we go. Titanium 4. And then this is oxide. You can tell my computer is getting annoyed with Photoshop. All right, and then the second one here, chromium with a 2+, and then sulfide with a 2-. Those already balance out, so we could just get CRS. And then we can name them. Chromium 2 sulfide. All right, and then the last one just says, I believe it just says break these into the ions. Yeah, so you don't have to make a formula out of them. I'm going to do that just for practice, just so you can see that. I don't know why I'm scrolling over there. I got to scroll over here. So gold 1 chloride, we'll just draw a line. And I've capitalized the first of the sentence. I really shouldn't have. I should go back and fix those. Wow, I didn't even try to write that. There we go. So gold 1 is this. Chloride is this. And then I can balance out the charges. Just need 1 of each, so there you go. And you notice that I'm starting to mix in elements that do not need Roman numerals and elements that do, because you're going to get just a random assortment of them. Sodium nitride here. Sodium is Na+. Nitride is N3-. I need a bunch of these. We've done sodium nitride several times before. It is a fan favorite. There you go, Na3N. Got barium oxide, so here's barium. What do you do with a dead chemist? Yeah, barium. Boom. There you go. Stupid jokes aside, you know. And then finally, platinum 4 fluoride. Platinum 4 is PT4 plus. Fluoride is F minus. I need a bunch of these. There you go. All set. Let me know if you have any questions about that. Okay, so we have 15 more minutes, and I'm almost done with the chapter, so let's go finish this off. All right. The last exercise that I have for this is, what do we do if we want to include polyatomic ions? Now, it says anions at the top, but there is one cation. They're just all the rest of them are anions. Now, the polyatomic ions list that I gave you was at the beginning. Oops, I hit the wrong button. Of the slides for this chapter. Here's all my polyatomic ions. And basically what we do for any compound that contains polyatomic ions is that you just drop the name of the polyatomic ion in the box that it appears in. So when I say the box, I mean the naming box. So if you have ammonium, you would just drop ammonium in this box. And if you had any polyatomic ion that was an anion, you would drop it in this box. And you don't change its name in any way, you just use the name of the ion. All right. So let's do that. For instance, what would I call this? And so you might not actually know what this is without looking it up. And you might not know that it's 2 minus, but you do know that these potassiums are +1, so you could deduce it. Now, if you don't know what the polyatomic ion charge is and it's paired with a transition metal, then you have to go and look up the charge of the polyatomic ion in the table if you haven't memorized them. But now it's just a matter of naming. So this would be potassium. And this would be carbonate. And so the name of this would be potassium carbonate. So you just take the name of the polyatomic ion and drop it right in there. You don't have to modify it. You don't put "ide" at the end unless it already has "ide." You just name it as it is off that table. All right. So this next one, I'm going to have you look up the polyatomic ion name and try and figure out its written name. What would you write out for it? Okay. Go ahead and type your answer in the chat. I'll give you like a minute or two to do that. If you have the slides for chapter 4, I obviously feel free to scroll all the way back to the beginning and look at those. Or you can scroll back in the video like 30 seconds or so. All right. Hopefully, you were able to find that this is that. And that we would name this one barium, because that one's not new. And this one is hydroxide. All right. So I have more of these. And I have more of these on the next slide here. We're going to do this page of them, because that's going to be all the time that we have. So I'm going to give you 5 minutes to try these. And you can type your answers in the chat as you get them. And then I'm going to leave the rest of them for you to practice, because I have a few more slides after this, but it's really just more practice on this sort of thing. So go ahead and try these. I'll give you 5 minutes. We'll go over the answers together in just a bit. All right, we are almost out of time, so I am going to go over the answers here. So we got NH4, which is ammonium. And then SO4 is sulfate. Excuse me. Ran out of water here. I need to get more. We got potassium. And then this is called hydrogen carbonate. We got sodium nitrate and lithium cyanide. So again, just naming the things that are present. You can actually do that without splitting them into ions, but if it helps you, you should. Down here, I'm absolutely going to write them as ions because we need that information to make the compounds. So I've got sodium and then hydrogen carbonate, +1 and -1, so I could just stick them together. We've got ammonium chloride. Same thing, same charges. I could just put them together. And then potassium and then phosphate look like this. Need more potassiums here. K3PO4. There you go. I'll let you... You can pause the video if you need to write this down, actually, because I'm going to go to the next slide. I'm going to just give you the answers here, in case you want to do these on your own. I got to think about this one. Phosphate is... Okay, so... There you go. So there's the answers to those that you can do on your own if you'd like. The last few slides deal with parentheses, so only include parentheses if there is more than one of a polyatomic ion. So if you have multiple cyanides, use parentheses. If you have multiple hydroxides, use parentheses. Otherwise, you can see up here these two. There was only one of the polyatomic ions, so parentheses were not necessary. Only use parentheses if you absolutely have to, because there's more than one polyatomic. Okay, and that's it. That's chapter 4. So the last... Oops, I don't know why that's doing that. The last few slides talk about that a little bit more, and they have more examples that you can do. So that's it. I don't know if this is going to actually make a noise, but oh, there's the last homework practice. Like yeah, there are 60 or so problems for you to do of just naming. So do as many of those as you can in preparation for quiz number 4 and the midterm, which is next week. All right, that's all I got. Hooray! All right, I do want to thank everybody for coming out to the extra lecture. I realize it's obnoxious to be here for 3 days a week because really we've kind of signed up for 2. It does sometimes happen, and I appreciate everybody being here and participating. If you're watching the video afterward, also totally fine. Make sure that you get to me with any questions that you might have about... oops, that didn't load. There it is. About anything that you have in Unit 4. On Monday, we are going to start Unit 5, Chapter 5, sorry, there are chapters in this class, which is Covalent Compounds, and my goal is to get that done that week. I think it's pretty possible. So yeah, that's really all I have here, so I hope everybody has a wonderful weekend. Happy studying. Make sure to get quiz number 2 in tonight. It closes tomorrow. Quiz number 3 is due next week. Take care.